Good evening, dear student, and welcome to this other edition of our stochastic processes class or tutorial. So today our tutorial will be about conditional expectation and Martingale. So I'm going to write the first application or the first example that we are going to do today. So the first question or the first problem that we are going to solve we are given the following. We are given a probability space. Remember that a probability space is a triplet. A probability space is a triplet where you have a non-empty set. Omega. You have sigma algebra F, and you have a probability, which is a measure. Actually, a probability space is a probability. You have a sigma algebra and a non-empty set omega. In our case, omega will represent the sample space, right? So the sample space omega is given as -1, 0, and 1. So it's finite. And the sigma algebra F, in our case, in this problem, is the power set of omega. And finally, we define our probability measure to be uniform probability. Uniform probability, you have 1, 2, 3, and the sum is equal to 1, so it will be 1 by 3. So the probability of each so we have the probability of the event, -1, which here is an atom. So it will be equal to the probability of the event 0, which is equal to the probability of the event 1. So we have a uniform probability, be 1 by 3. Okay, so now with this one, we define two sub-sigma algebra of F. So we define two sub-sigma algebra G and H of F, or the power set of omega, such that the first sub-sigma algebra G is made of the following set. You have the empty set, and you have two atoms, -1, zero, 1, and omega itself. And we have the sub-sigma algebra H, which is made of the subset of omega, the empty set, two atoms, -1, 0, and 1 or positive 1. And finally, omega. So the two atoms here, we have two atoms from G. We can call the first one maybe A1, which is the singleton made of -1, and A2, made of the single or the pair 0, 1. Okay, so in this case, we also have maybe we can call E1 and E2. So E1 is -1, 0. E2, +1. So what are these called atoms? Atoms are actually the minimal non-empty measurable sets, right? They cannot be divided further, right? They have to be non-empty, so the empty set cannot be bigger, have to be non-empty. And the atom means that they cannot be divided further. If you take omega, you can divide omega further, right? And any other set or any other subset can be obtained from these by union. Like for instance, omega can be obtained by taking the union of A1 and A2. If you take the union of these two, you get omega. So omega is not an atom, these are the atoms. For G, the subsigma-algebra G, A1 and A2 will be atoms. And for H, the subsigma-algebra calligraphic or cryptic H, the two atoms will be -1, 0. That is E1, and E2, the singleton +1. Right? They cannot be divided further because if you divide further, you will not obtain an element of the sigma algebra. Right? You cannot divide this further. And if you take the union, you can get other element like omega itself. Right? You have to be non-empty, so the union cannot give you obviously the empty set. Right? So these are atoms. And these are building blocks actually of your sigma algebra. So any other building block except the empty set at omega will be our atoms. And they will play a crucial role into computing conditional probabilities, as we are going to see very soon in the problem at hand. So what is the problem now? So first of all, we are going to define a random variable x. So we define a random variable x such that for any omega, in omega, for any element of omega, x of omega is omega, x of omega is omega. So meaning that actually omega here will be the identity, the identity function of omega. So this is the question. We're asked to compute compute first the expected conditional expectation of x given g given h. So actually this is what we call an iterative expectation. So that's the first, and the second problem is to compute. We are just going to interchange G and H. That is conditional expectation of the conditional expectation of x given h given g. So we are computing the conditional expectation given g of the conditional expectation of x given h. And the first is we are computing the conditional expectation given h of the conditional expectation of x given g. So in order to compute this, generally, we know already that by definition of a conditional expectation, it is a random variable. And for a random variable, we compute, okay, let me denote this. I can call this y and this z, right? So I can say, for instance, let y equal this, right? Okay. Yeah, I think I will be able to copy that easily, which is good. Great. So copy, paste. So this is our y. We know that the conditional expectation is a random variable, and we are going to define z or z to be the conditional expectation given g of the conditional expectation of x given h. So if we define each of them, we know that a random variable is defined for any omega element of big omega. So actually, that's what we are supposed to do. But that might be complicated or a bit difficult to do. But the best way to do the computation is to look at, we are going to compute, because actually what are we looking for? We want to determine W omega and Z omega for any omega element of capital omega. So we want to find y of omega and z of omega for any omega in omega, right? Actually, what does that mean? We will be computing y of singleton 1, y of singleton 0, y of singleton 1. I repeat, from this, if you take each element of omega, omega will be equal to -1, 0, and 1. I will be computing x and y of each of these elements, right? But it will not be efficient if we do that, right? Since we are computing with respect to a sigma algebra, since in the sigma algebra we have these atoms, you see that if you take this atom, each of these elements, -1, 0, and 1 are already part, right? So if I compute on each of these atoms of G and H, I will compute everything, and it will be easier for us to do that. Why? Because this form a partition, right? These two atoms will form like a partition of omega. We see that this is non-empty, this is non-empty, and if I take the union, A gives us omega, and the intersection is empty. Similarly, these two also, E1 and E2, will form a partition of H, right? Each is non-empty, the intersection is empty, and the union gives us omega. Okay, I think it's easy to put it that way. And if you recall from what we saw in class, if we have a sigma algebra that is finite, right, and if you recall, let me quickly recall that here. Recall, if B is a sigma algebra, right, generated by a finite number of set B1, B2 up to Bn, right, where Bn form a partition of omega, then we can easily compute. We know how to write the conditional expectation of any integrable, of course. X has to be integrable, meaning that the expectation of the absolute value of X has to be finite. Okay, with respect to this sigma algebra, we have a nice formula to compute that. It will be the sum, right? It will be the sum over J running from 1 to capital N, expectation of the product of X with the indicator function of Bj, right, divided by the probability of Bj, right, into Bj. Actually, this as a random variable is what we will call simple random variable. So this is a simple random variable. Simple, why? Because it's a linear combination of indicator function. And you can see that this is actually measurable because Bj is measurable. Bj is an element of the sigma algebra, as we can see here. It's one of the generator of the sigma algebra. So a linear combination of indicator function of measurable set will be measurable. And we know that by definition of the sigma algebra, a conditional sigma algebra, it has to be B. So this EXB condition on B has to be B measurable. And that's exactly what we can see here. So now that we have the Bj, which are the atoms for each B, it becomes easy to use this formula to compute this. Using this formula, the computation of our conditional expectation becomes very easy. So I think now you can see the reason why it's better to decompose, our omega, our G into atoms, right? Or partition of omega, right? And then we use this formula. In the case, of course, our omega is finite, it becomes easy to compute a conditional expectation with respect to a sigma algebra. So, now that I've already defined each atom, so the first question, you can see here that the first question, we will first compute. So yeah, there are two steps. We will first compute the conditional expectation of X given G, right? And once we get this result, which is a random variable, we will proceed by computing the conditional expectation of this random variable given H. So for the first one, we will look at the atoms of G. So So for the solution, the first thing you are going to do will be the first question here, where we are computing the conditional expectation given h, right? Given h of the conditional expectation of x given g. So as I said, there are two steps. We will first compute the inner conditional expectation. We can call this maybe x prime. And once we obtain x prime, we will proceed by computing the conditional expectation of x prime given h. So you can see that in each case, we will consider the given sigma algebra, right? So in the first step, we are going to compute x prime, which is the conditional expectation of x given g, right? So we're going to consider the sigma algebra G, which we know to be made of the empty set, the singleton -1, and finally the singleton 0 +1, and omega. So these are our two atoms, which I remember we call sorry, A1 and A2. Yeah, A1 and A2. So we have our A1, which is -1, and A2 is 0 +1. So these are the two. So we are going to dive straight into the computations. So we take an omega, we take omega for, because we want to compute for any omega, in capital omega, right, for little omega. So since we already have our two atoms, we are going to consider these two atoms, right? Because if you take our element in each of the atom, we will cover omega. So for omega, in A1, which is the singleton -1, if you recall this formula that I wrote here, this one, you see that here we are fixing our bj is just one of them, right? Because this is one of them, we take just one. So meaning that we will just take our j equal to 1. So because we will apply this at omega, right? Because if you take omega here, this will be the sum with omega, but since omega is in B, I mean in A1, you can replace this B with A. So since omega is there, let me write this. I think it would be better to do that. So if I take this formula, so if I apply omega to this formula, now I can replace the BJs we just with AJs. You see that here I write AJ. This will be AJ and this will be AJ. Right. That will be omega. But we know the definition of indicator function. So if omega is not in this, we just have two omega. They are only, the partition, since there are only two elements in the partition here, omega here is A1 union A2. So you see that this summation will give us the sum j equal to 1 to 2, conditional expectation x, indicator function aj, by the probability of aj, indicator function of aj, omega. So if I split this, right, it's long what I'm doing. I could have just shortened the notation, but it's always good to write everything to make the thing easy to understand than to try to skip. Now, if I split the sum into two, you see that I'll have the expression with j equal to 1. So you can see that this will be 1, 1, 1, and then plus the same thing here. But this time I replace j with 2. So here we have indicator function of A2. And this is indicator function. But we know that in this case, we took omega in A1. So omega is A1 is not in A2, right? Because they are disjoint. So it's not in A2. I need to quickly connect my battery because unfortunately, I'm sorry. I've just realized that the battery is indicating. I hope it will not go off. Okay, thank God I succeeded to connect. Okay, good. So we can proceed. Okay, now you see that this omega, we took omega in. Omega is taken to be an element of A1. So omega is not in A2. So definition of an indicator function, this will be equal to 0. And this will be equal to 1. Definition of, oh, sorry. It is not in A2, so since it's not in A2, indicator function of A2 is 0, and the indicator function of A1 of omega is 1. So you see that this will reduce to 0, and since this is equal to 1, the entire expression would just be so this entire expression will be reduced to expectation of the product of x with the indicator function A1 by the probability of the event A1, because this is 1. Okay, now what's the probability of P1? Of the probability of A1 is mu, right? This will be mu. Obviously, this one, since this expectation x is discrete, x is discrete, x is discrete, and P of E1 will be reduced to mu of the singleton -1. The singleton -1, and by definition, we know what he represents. Mu of the singleton, anyway, mu of any singleton, because P is mu, is 1/3. So I can go back to this expression and replace to get a value. So if I rewrite, this gives us expectation of x. Of course, A1 is -1. And P of A1 is mu of the singleton -1. So this will give us, we know the result of that. And this one, since it's discrete and it has one element, we know what is the definition of the expectation, right? We know that it takes this value -1. So it will be x at -1 times the probability of -1. So this is x. For x of -1, if you want. So that's the value of omega, times the probability, which is mu. Mu, now it's mu of, not of a point, but of a set. A measurable set, which is our -1 here. So divided exactly by the same thing, mu of -1 And you can see that these two will cancel out, and we are left with x of -1. And you see that with this one, the computation becomes very easy. We know that x is identity, so that's -1. So the good thing with this is that when we compute this, like at a point, our point here, omega is -1, it will give us the value of the function of the random variable at that point, right? That is when our atom has just one element. The conditional expectation will reduce to the evaluation of the function at that singleton. And if it has more than one and it's finite, it will be the average value of the function or the random variable on that set. So we have already this. So we'll move to the next one. Now, for the second case, now we are going to take omega in A2, right? And we know already that A2, what is A2? Is 0, 1, or 0, +1. So that's the second case here. So now if we take omega in A2, which is 0, +1, we do exactly the same thing. I'm not going to repeat what I did above. We use exactly the same formula. We split, and we see that the formula will be reduced to this one now. Our formula this time around, it will be reduced to the second one. That is with 2 here. So I will copy this. That was the advantage of doing what I did previously, so that I will not repeat the computations. So I can now write here that this will be equal to so for A2, study will reduce to E2 here. E2, which in our case will be expectation X. Now our A2 is 0, +1, divided by mu and since there are 2 elements here, we are going to, this will become a sum of the value of the function x at each point times the corresponding probability divided by this. You see that I give us an average because there are 2 elements, so and you have a sum on top. So this will give us now if I expand this, it will be x at 0 times the probability of the singleton 0 plus evaluation of the function or the random variable at +1 times mu for the probability of that divided, of course, by the sum, because this is a probability, so it will be the sum of the singletons, right? We are going to break this into two. So probability, that will be sigma of the singleton 0 plus, I mean mu, not sigma, mu. Right? Obviously, this singleton, right? Let me quickly explain. So this singleton can be written as the union of two disjoint events, right? These two. Now we know that if I take such a probability, so mu of this would be the sum of the two. So that's exactly what we are doing here. So now if you substitute, remember that this is an identity, so it will be 0 times that. So the first part will be 0 plus, this will be 1 times this. Mu of that is 1/3. And this one is 1/3 plus 1/3. So actually it's 2/3. So it will be 1/3 divided by 2/3. So we simplify the 2 is 1/2. Okay. It's 1/2. And if you remember what we said, what I said is that if you evaluate here on this atom that has two elements, it will be the value of the average of the value of the function at the 2 points. But since this is identical, I mean, it's the identity, meaning that mu, x0 plus x1 divided by 2. That's the average, right, of the function. So that will give us x of 0, which is 0, plus x of 1, which is 1. So that will be 1 by 2. That's exactly what we have here. Okay. So now we can conclude. We can conclude for that question that the conditional expectation of x given g will be equal to, of course, I will write that at omega, because this is a random variable. I have to write it for each value of omega. So this will be equal to -1, as we saw for the first time, if omega only takes the value -1. And it will be 1/2 if omega takes either value 0 or 1. So in other words, we can say that conditional expectation given g of x at omega, if omega is equal to -1, it will be -1. If omega is equal to 0, it will be 1/2. If omega is equal to 1, it is 1/2. You see that using atoms, we don't need to split the case omega equal to 0, omega equal to 1. Then we take the atom, which is given by this, and we get the same value for each one of them. It makes life easy. All right, so that was the first step. So the second step, so remember that we said we first compute this. Actually, this is not yet the final answer. This is a partial conclusion. This is a partial conclusion. So now we are going to compute. I think this should be step 2, if I'm not mistaken. So what did I write on top? Okay, so this was step 1. We compute this. So that's our x prime. Now, step 2, we are going to compute the entire expression. So this is x prime. Now step 2. Now in step 2, we are going to compute the conditional expectation of x prime given not g this time, but h. So we repeat exactly what we have just done. We're just going to repeat exactly what we have just done because we know already what this is, x prime. X prime is given by this. So we have already our x prime, our random variable x prime. We know all the, it's no longer identity. Remember that with x was identity. That is x of omega was omega. Now x of omega will be different from omega. X of omega will be omega if omega is -1. But x of omega, x prime of omega will be 1/2 if omega is either 0 or 1. So it's no longer the identity. So we are going to repeat exactly what we did above. Now for H prime, for G, we have our 2 atoms. So for H, the atoms are B1. Oh, I use E actually instead of B. I use E. So we have E1, which is -1, 0. And we have E2, which is +1. So these are our 2 atoms. So we just repeat what we did previously. So we know that if omega belongs to E1, meaning that if it is either -1 or 0, now we are going to compute E of omega, this conditional expectation of x prime given h. We know already that at omega, since we have a sum, and the sum will be split on the x1 and x2. Since it's in E1, E1 and E2, since we are computing the sum or linear combination of the indicator function of E1 and E2, omega being E1, it will be reduced to E1, to this one. So meaning that if you copy what we wrote above, so this will give us expectation of x prime into indicator function of E1, indicator function of E1 by the probability, of course, of E1. And we know that our probability here is in terms of mu, because that's what we need here. So if you replace this will give us this will give us E of x prime indicator function of -1, 0. That is the set by mu of this set or event, like this. We know already that it will be the sum of the two, which will be 2/3. Right? Okay, now we can split this, it will become a sum. So that will give us In the numerator, we'll have x prime of -1 mu of the singleton -1 plus x prime of 0 into mu of the singleton 0 divided by the sum of these two, which is 2/3, as I already said. Okay, but let's write it down. So this will give us. Okay, so now we can read the value of x prime of -1. If we recall from above, we saw that it was -1. So this will be -1 into 1/3 plus, and this one at 0 is 1/2 into 1/3, and the sum of the two will be 2/3. Okay, so let's look at it. So what I'm saying is that x prime of -1 is -1, and for the other two elements will be 1/2. That's why we can see here it will be -1 and -1, and 1/2 if not elsewhere. So if I substitute, obviously I can factor by 1/2, as you can see here. If I can factor by 1/2, I can cancel like this. So I factor by 1/2 and I cancel, right, with this. And now on top we have -1 plus 1/2 is -1/2. -1/2 by 2 is -1/4. So the result gives us -1/4. So that's what we get for this case. And if omega, if you repeat the same thing here, if omega is in E2, we get exactly the same thing but with E2. I'm sorry. I think I did, but it's, oh, no. If I do this, okay, good. So I made a mistake. Sorry for that. Okay, so I'll copy, okay, let's copy up to, okay, let's even copy everything to make life easy for us. Right. Okay, now if we take, we simplify and make life easy. This is E2. Anyway, so this is what we have here, omega there, then this will be E2. Here, this will be E2. E2, E2. That's what it will give us here. So E2, this will reduce to that and that. Okay, so as we know already, So this will give us is only one element here. So this will be x prime of 0 into mu of the singleton 0 divided by that. You see that there's only one element, so it will give us, you see that if we simplify, it gives us the value of the random variable at the point, right? Because omega is just 0, that single value. Right? And we know that this is 1/2. So now we can conclude, right? You can write our final conclusion here. So if you replace the x prime, we have x prime. Remember that x prime is the conditional expectation of x, right? Given a g. So this will give us, we know that there are two values, negative 1/4 and 1/2. Those are the two values. So it will be negative 1/4 if omega takes one of the values, -1. What have I done here? Sorry, this is not 0. This is +1, right? Sorry. Right? -1. This is +1, not -1. What did I even say? So what did I say at 0? Oh, okay. This is 0. I think I wrote something that was not true. When I said that x prime of 0 is 1/2, that was not true. Huh? Let's look at here. Oh, yes, it's still 1/2. Okay. So, okay, good. It still worked because, okay, good. Okay, this is -1, 0. And for 0 here, yeah, it was 1/2. Okay, good. So I think I made a mistake here. It should be +1. So +1. But what is good here is that it doesn't change the result. Otherwise, anyway, but what I wrote previously was wrong. Just imagine that the result were different. I would have gotten a wrong answer, but thank God, the result will remain unchanged. So x prime of 1 and f prime of 0 is the same, so that's why we don't have any issue. That's why we don't have any issue with our computations. But the correct procedure is this. So x prime of 1. So this -1, 0. And it is equal to 1/2 if omega is +1 or 1. Yeah. So that is it. That is it for this. We have the complete random variables that have been computed here. Now, similarly, I'm going to give you the result for the next problem, but you are going to do the computation yourself to make sure that you obtain exactly the same value, right? So I would just say similarly, and that will be homework for you. So similarly, now if I interchange the two sub-sigma-algebra, meaning that if I compute the conditional expectation given H, no, G. Now given G, of the conditional expectation of X given H, we are going to get the following results. So here we look at this. The atoms of I think it was -1. Yeah, it was -1. And then we have 0 plus 1. So these are the atoms of G. That's everything, because remember that this is, if you call this X or Y prime, you call this Y or Y prime. At the end, we will compute with respect to the atoms of G. So, and those results will be written here. Given the atoms of G, which are -1, 0 plus 1. So the first one, for this one, this will be -1/2. And for this one, will be 1/4. Obviously, as if we interchange these two results here with the negative sign to the, okay, so we interchange, we keep the negative sign, we interchange. That's just a coincidence, huh? Don't just go and say that I say that's how it should be. Not necessarily. Okay, so that is it for this conditional expectation. Right? A good example that will allow you to actually understand further how to compute this. I think I will stop here to make the video. It's already long, but I will make it shorter, and I will continue very soon with the second part, where we are going to talk about Martingale. Right. And probably I might add extra problem later on, but so far so good. I think we will stop here for now, and very soon I will continue with the next part to make, just to shorten the video. Okay, thank you so much for your kind attention. God bless you, and see you very soon.